Section 14.5, excuse me, we're going to take a look today at volume, okay? We did surface area in the last section. Surface area, typically speaking, is more complicated to find than volume. So that's good news. The volume is usually an easier computation to make because we have one formula, typically speaking, for the volume as opposed to two pieces of a formula, right? With surface area, we had the lateral arrow and we had the bases, and then we had to combine them somehow. All right, so the first thing I would like for us to take a look at is what we mean by volume. So volume refers to the number of cubic units needed to fill a three-dimensional surface. So the volume is, the soda inside of the can, whereas the surface area is the metal aluminum around the can. That's the difference, okay? And both are important, obviously, if you're creating the soda can. You want to make sure you've got the space inside. You want to minimize the cost of the aluminum on the outside. So both quantities are things that we need to find information about often. A cubic unit is the amount of space taken up by a cube, which measures 1 unit on each side. So it's a 1 by 1 by 1 cube. So imagine a dice, right, or a number cube. And you've got 1 by 1 by 1 centimeters or inches or whatever. So starting with, let's take a look at this. And we're going to find the volume and surface area of this object. Volume is the easy one. What is the volume of this object? Yeah, it's just 4. All you have to do is to count the cubes, right? Sure. So this is 4, and this is units cubed. Surface area, that's trickier. So let's see what we have. Well, from the front of the object, what's the surface area? I think it's still 4. Yeah? So if I look at the object from the front, I get 4. And it's also 4 from the back then, right? So I'm going to get 4 plus 4 from the front and back. And then we have to start, sort of changing our perspective of the object. So let's look at the object from this side. If I'm looking at this object from this side, I have 1, 2. Okay, so I'm not looking at this piece. I'm just looking at from a two-dimensional side of the object. So I get 2 from this side, and then from this side I get another 2, right? So I have 2 plus 2. So I've done front and back and the two sides. Now I need to do from the top down and from the bottom up. So from the top down, what do I see?
3.
I see 3. And from the bottom up, what am I going to see? 3. And these seem to be occurring in pairs, don't they? Okay? That doesn't always happen. We're going to see an example in a moment when it doesn't. But we'll clarify sort of when it does and when it doesn't when we look at that example as well. So if we count these up, what do we get? 18 square units. And do we all agree that the volume was much easier to calculate than the surface area? We didn't have to change any perspective at all, right? It was pretty simple. All right, I'd like for you to give a try for these two. Now, my image on the screen has some color to it, which might make it easier to look at. If not, yours is all grayed in, and I'm sure it's fine too. But you're finding the volume of each and the surface area of each. So we'll pause to let you take a look at that one. A couple things about this image to not be worried about. You can't really see if there's a cube underneath the blue one on the left-hand side. There is. Okay, so we're not assuming that there's any holes that are weird and people are trying to trick us. That's not our goal here. Okay, so it is sort of filled in. And this one right here, as they stack, they almost don't look like they're quite measuring at the exact same corners. They are. It's just the way that things are manipulated when you work inside of Microsoft Word and PowerPoint and stuff like that. Okay, so don't try to overcomplicate the image that's already kind of funny looking. How was finding the volume? Easy, right? I mean, that was the easy one, right? What did you notice about the volume of these two shapes? They're the same. So what did you get for the volume on these? Okay, and then what happened between them, of course, is they picked up the blue cube and they moved it. And that didn't affect the volume, of course, right? Because the volume is the space inside. But did it affect the surface area? It should have affected it. Now, if you didn't think it affected it, it's probably because you didn't know what you were supposed to count exactly when you were doing the surface area. Let's do the surface area of the first figure because it's a little bit easier to count than the second one. So if we do the first figure's surface area, do you notice that things occur in pairs again, kind of like the last image that we did? From the front and from the back, from the top and from the bottom, from the left and from the right, you get the double image. Same image from both sides. You know, when you look at the two-dimensional side of it, it's the same. So if you look from, let's do from the front. And so when I say front, I mean the part where I see the fronts of these shapes. So my front is kind of looking at it like this. Okay, the front side of this, how many do I have for the surface area? I have 6. Does everybody have 6? So I have 2 times 6 because I've got the front and the back that are both 6. All right, let's do from the right-hand side. So that's this way looking at this thing. So if I look at it from the right-hand side or the left-hand side, either way, so looking at it from here or from sort of this hidden view from the left, kind of looking at it backwards this way, what do you get? You have 5. Did everybody get 5 on that one? Good. So that's 2 times 5 because I have the left-hand side and then I have the right-hand side. And then we're going to do from the top down or from the bottom up. So if you look at this from the top down or from the bottom up, how many do you get? It's 6 again, right? And you can see it almost from the top because you can count the tops of these guys. 1, 2, 3, 4, 5, 6. You're seeing from the top down. So this is another 2 times 6. So if I add all these up, what do I get? 34. And it's square units on this one, right? Okay, now I actually have a very similar description. I have all of these same surfaces when I look at the other image. Okay, I really do. I have all these same surfaces. They're shifted a little bit. But I have additional surfaces that I didn't have before. So let's look at it piece by piece again. So let's look at from the front. So looking at from the front, I have 1, 2, 3, 4, 5, 6. From the front and back, I have 12. So 2 times 6. From the right-hand side, looking at it, over here, I have 1, 2, and then I have this 3 up here on top, 4, 5. So I have 2 times 5. From the top down or the bottom up, I have 1, 2, 3, 4, 5, 6. So what have I not counted? Does anybody know? Yeah, it's this little piece inside that when I focus only on the two-dimensional part, I don't get to see that, right? So in fact, I get this piece right here's area. I have this piece's area, and I have the other side of this blue cube's area. There's 3 sides that are missing because they're concave is what they are, right? They're sort of sandwiched in the middle there, and I can't see them if I only look two-dimensionally from the sides of the object. So I'm missing 3 of these. So this one ends up being 37 units squared. So the part about this one that makes it not like the other one is that sort of cavity, that cave-like shape that the other one didn't have. That's the difference. So when I don't have that cave-like shape, I have these things coming in pairs, just like in the last problem too. But when I do have that cave-like shape, I have to be a little bit more careful. All right, after we did a hard one, let's do a Rubik's Cube. What's the volume of a Rubik's Cube? Can't exactly count this one. It's not like the last image, right? You don't see all of them. What is it? 27. How'd you get 27, Jacqueline?
Because if you take it by the 3 slices, and there's 9 in each one. So 9 times 7.
Okay, let me get a color that will work on this because I've got so much color on the screen already. That might be dark enough. I'll make it thick. So if I spliced out this piece, I think is what you're saying. There's 9 there, right? There's 9 along that section. There would be 9 along the middle section right in here as well. And then it'd be 9 along the back section, and 3 9s added together is 27. Do you guys see that okay? Okay. So that's what it looks like to talk about the volume of a cube. How could I do that in terms of a formula instead? I think we get to it later, but we'll do it right here and now anyway. What do you think we'd have to do to get that from this picture's shape if I did it without splicing it along each of those? Okay, so in each case of this one, there are 3, right? 3, 3, 3. So 3 times 3 times 3 is 27. That actually works very nicely for any rectangular shape. This one happens to be square, right? It's a cube, actual cube. So this one is actually side cubed. But in general, we would have length times width times height. We just happen to have one where the length, width, and height, they're all matching right now. So it's side cubed. Okay, a few more things before we go. Units of volume. I've been thinking the last couple of days, and I'm not sure I've come up with exactly the solution I want right now, but it is not reasonable to ask you to memorize or use up card space for infinitely many tables that we seem to keep having in here. So I'm thinking about how I want to handle that. I'll let you know next time because we're doing a review for the test next time as well on how to handle that. There's no tests that you take that assume that you know some of these measurements. Now, tests you take will assume that you know that there are 3 foot in a yard and 12 inches in a foot, some of those basic kinds of things. But nobody's going to expect you to know how many cubic feet there are in inches cubed. However, some of those you could calculate as you work through it on your own. A few of these, though, are ones where you wouldn't. For instance, gallons. 1 gallon is 230 cubic inches. 231, sorry. That's not something that you're just going to remember. Now you might, because I just told you you're not going to, but you know what I'm saying, right? The quart. A quart is 1/4 of a gallon. That's great, but it's 57.75 cubic inches and 32 fluid ounces. Well, the 32 fluid ounces, you might remember that one. I've got a memory aid for that one here in a second. But the cubic inches in the middle, that might be kind of a stretch. So some of these are ones that you probably remember, some of them are ones you don't. So I'm going to talk to you on Thursday about what it is that I expect you to remember or to write down for yourself if you don't remember them and what I'm not. Have you guys seen this guy before? Well, I've seen some nods. Who has seen it? Raise your hand for me. Jacqueline, Emma, Allie, anybody else? Okay, so I saw Jacqueline nod her head first. Do you remember what they call him? Gallon man or gallon guy is what I've heard him called. This is the cutest thing like ever. If you do any of your observations in a middle school, you'll probably see this guy in the middle school. That's where I've seen him, and I've seen him there pretty recently, in fact. So here he is. He's 1 gallon in the middle. Okay, do you see his gallon body in the middle? And his gallon has 4 quarts off of him. There's 4 quarts in a gallon. Okay, and off of each of the gallon, we have the yellow pieces. These are pints. 2 pints in a quart. And then off of each of these pints, we'll take 1 single pint, we have 2 cups. So a lot of times what I'll see happen, and this is just in my observations with my student teachers at middle schools, is I see kids having created this themselves. So it's decorating artwork in some teacher's classroom, basically. And they've created their own gallon guy. My daughter created a gallon guy. She was younger than that, though, because I remember her bringing it home, and it was massive. I mean, like they had cut out pieces of paper. Like the ones that I've seen recently were all on 1 sheet of paper, nice and neat, kind of like this little guy. Hers was massive, where they actually cut things apart. So they started with the size of a gallon, and they cut it into fourths. And then they had 4 quarts. And then they took this quarts, and they took images, pictures that were the exact same size, and then they cut those in half. And those were their 2 pints for each of those. Then they took the pints, and they cut them into, like it was actually a guy. I should probably bring in that picture next time if I can find it. I don't still have the object she created because, like I said, it was kind of awkward. But pretty cool. Pretty cool, massive image that she will remember as she's looking at the relationships between these. And so it's all ratios of 2s and 4s, right? Everything up here is ratios of 2s and 4s, or 8s, depending on your perspective of what you're looking at. So this is gallon guy, okay? Let me see here. Let me do one more table, and then we'll start in on some problems next time. One more table here. These are metric units of volume. These aren't terribly difficult to create on your own if you were to need them for the most part. A few of them are a little bit different though. So like for instance, it says 1 centimeter cubed is the same thing as 1,000 millimeters cubed. And we talked about in the surface area section that when it's area, if we were supposed to move it 1 decimal because we're doing it squared, we move it twice, right? So if it's volume, we're going to move it 3 times. So a centimeter relationship is that we have, if we go from centimeters, if we have 1 centimeter, this is equal to 10 millimeters, right? We moved the decimal 1 place. So if you're going from cubed, you move the decimal 3 places. That's where the 1,000 is coming from instead of 10. Okay, it's supposed to be moved 3 times. The part that's a little bit interesting is that 1 millimeter cubed, I'm sorry, not 1,000 millimeters cubed is 1 milliliter. Okay, milliliter, and I don't remember if you guys had a measurement on that one where you, it's like an eyedropper, okay? Eyedropper kind of thing. It's very, very, very small. So 1 milliliter cubed. And then you can, 1 milliliter is 1,000 millimeters cubed. And then the other ratio down here that's a valuable one we're going to use next time is that 1 liter is 1,000 centimeters cubed. So those are relationships that are a little bit trickier to work with, not quite so obvious, and you see other relationships in here. Here's the 1 liter, here's the 10,000 or 1,000 centimeters cubed, here's the 1 decimeter. Can't get my meters and liters coming out of my mouth right. 1 decimeter cubed as well. So we have this relationship somehow between cubic space and capacity, and that makes sense because that's what capacity is. It's volume. It's what fills something up, right? So there is that natural relationship that should be happening there. When I find the volume of the can, it should be length times width times height. Well, that's linear measurements. I get cubic things, right? But when I fill it up with the actual liquid, I get ounces or liters, and that's what's happening in this chart. So next time we will take a look at actually doing some conversions in volume.